The fractional quantum Hall effect, FQHE, is a fascinating and complex phenomenon in condensed matter physics. It occurs in two-dimensional electron systems subjected to low temperatures and strong magnetic fields. One basic concept. The FQHE is an extension of the integer quantum Hall effect, EQ. While the EQ involves the quantization of the Hall conductance at integer multiples of He2, where E is the electron charge and H is Planck's constant, the FQHE involves quantization at fractional values of this unit. This means the Hall conductance takes on values like 31 He2, 52 He2, etc. 2. Electron interactions and quasiparticles. In the FQHE, the electrons interact strongly with each other. These interactions lead to the formation of new quasiparticles that carry a fraction of the electron charge. For example, in the state with a filling factor of 31, the quasiparticles have a charge of 3e. 12 of these quasiparticles are neither fermions nor bosons but exhibit anyonic statistics, meaning they have properties that are intermediate between the two. 3. Laughlin wave function. The theoretical foundation of the FQHE was provided by Robert Laughlin, who proposed a trial wave function for the ground state of the system at certain fractional filling factors. The Laughlin wave function accurately describes the correlated state of electrons and predicts the existence of fractionally charged quasiparticles. 12. 4. Experimental discovery. The FQHE was first observed in 1982 by Daniel Zouet and Horst Stormer in experiments on gallium arsenide heterostructures. They discovered that at certain magnetic field strengths, the Hall conductance exhibited plateaus at fractional values of He2. 12 of this discovery was so significant that it earned Zouet, Stormer, and Laughlin the Nobel Prize in Physics in 1981. 5. Topological order. The FQHE is an example of a system with topological order, a type of order that is not characterized by symmetry breaking but by global properties of the wave function. This topological nature makes the FQHE robust against local perturbations, which is why it is of great interest for applications in quantum computing. 12. 6. Ennius and quantum computing. The quasiparticles in the FQHE, known as ennius, have fractional statistics and can be used to perform quantum computations. Certain FQHE states are believed to support non-abelian ennius, which can be used to implement topologically protected quantum gates, making them highly desirable for fault-tolerant quantum computing. 12. 7. Current research. Research on the FQHE continues to be a vibrant field. Scientists are exploring new materials and conditions to observe the FQHE at different fractional filling factors. There is also ongoing theoretical work to better understand the microscopic mechanisms behind the FQHE and to discover new phases of matter with similar properties. 12. The FQHE remains one of the most intriguing phenomena in condensed matter physics, offering deep insights into the nature of quantum systems and potential applications in advanced technologies. Low temperature requirement. The FQHE is typically observed at very low temperatures, often in the millikelvin range. At these temperatures, thermal energy is minimized, which is essential for maintaining the delicate quantum states that give rise to the FQHE. Higher temperatures can introduce thermal fluctuations that disrupt these states. 2. Thermal excitations. As temperature increases, thermal excitations become more significant. These excitations can break the correlated electron states that are necessary for the FQHE. Essentially, the quasiparticles that exhibit fractional charge and anyonic statistics can be thermally excited, leading to a breakdown of the quantized Hall conductance. 3. Energy gap. The stability of the FQHE is related to the energy gap between the ground state and the excited states. This energy gap is a measure of how robust the FQHE state is against thermal disturbances. At higher temperatures, if the thermal energy exceeds this gap, the system can transition out of the FQHE state. 4. Experimental observations. In experiments, the FQHE is observed by cooling the electron system to very low temperatures and applying a strong magnetic field. If the temperature is too high, the characteristic plateaus in the Hall conductance that signify the FQHE will not be seen. This is why cryogenic techniques are essential in experiments studying the FQHE. 5. Quantum coherence. Low temperatures help maintain quantum coherence, which is necessary for the collective behavior of electrons in the FQHE. Quantum coherence ensures that the electrons can form the correlated states described by the Laughlin wave function, leading to the fractional quantization of the Hall conductance. Achieving ultra-low temperatures for fractional quantum Hall effect (FQHE) experiments is a significant challenge due to several technical and physical constraints. Here are some of the main challenges. 1. Parasitic heat leaks. Parasitic heat leaks are unwanted heat inputs from various sources that can raise the temperature of the system. These include material heat release. Materials used in the experimental setup can release heat, especially as they transition to lower temperatures. Microwave radiation. Radiation from higher temperature stages of the dilution refrigerator can leak into the system. Electrical leads, RF and low-frequency noise can couple through the electrical leads, introducing additional heat. 2. Cooling techniques. Achieving temperatures below 10 millikelvin (Mk) requires advanced cooling techniques. Some of these include dilution refrigeration. This is the most common method, but it has limitations in reaching sub-millikelvin temperatures. Nuclear adiabatic demagnetization. This technique can achieve temperatures in the microkelvin range but is complex and requires precise control. 3. Thermal isolation. Effective thermal isolation is crucial to prevent heat from the environment from affecting the system. This involves vacuum chambers to minimize conductive and convective heat transfer, radiation shields to block thermal radiation from warmer parts of the setup. 4. Material properties. The properties of materials at ultra-low temperatures can be unpredictable. For example, superconductivity. Some materials become superconductors, which can affect the behavior of the electron system. Heat capacity. The heat capacity of materials changes at low temperatures, which can influence the cooling process. 5. Measurement sensitivity. At ultra-low temperatures, the sensitivity of measurement instruments becomes critical. This includes noise reduction, reducing electronic noise to accurately measure the tiny signals from the electron system. Thermometry. Developing reliable thermometers that can measure temperatures in the microkelvin range. 6. Experimental setup. Designing and maintaining an experimental setup that can consistently achieve and sustain ultra-low temperatures is challenging. This involves complex engineering, precision engineering to ensure all components work together without introducing additional heat. Maintenance. Regular maintenance to ensure the system remains free of contaminants and operates efficiently. 7. Cost and resources. The cost of equipment and the resources required to achieve and maintain ultra-low temperatures are significant. This includes high costs. Dilution refrigerators and other cooling equipment are expensive. Resource-intensive. The process requires significant amounts of liquid helium and other cryogens. Despite these challenges, advancements in cooling technologies and materials science continue to push the boundaries, enabling more precise and lower temperature experiments. Modern dilution refrigerators have seen enhancements in their cooling power and efficiency. These refrigerators can now achieve temperatures below 10 millikelvin more reliably, which is crucial for FQHE experiments. Innovations include better thermal insulation and more efficient heat exchangers. 2. Adiabatic demagnetization refrigeration, ADR. ADR has been refined to reach even lower temperatures, sometimes in the microkelvin range. This technique involves the demagnetization of paramagnetic salts, which can absorb heat and cool the system further. Recent advancements have improved the control and stability of ADR systems. 3. Quantum dot refrigeration. Researchers are exploring the use of quantum dots as nanoscale refrigerators. Quantum dots can be engineered to absorb and dissipate heat at very low temperatures, providing localized cooling that can be integrated into FQHE setups. 4. Superfluid helium-3. Superfluid helium-3 has unique properties that make it an excellent coolant for ultra-low temperature experiments. Advances in handling and utilizing helium-3 have allowed researchers to achieve more stable and lower temperatures. 5. Passive cooling materials. Recent breakthroughs in passive cooling materials have provided new ways to manage heat without active refrigeration. These materials can dissipate heat more effectively, helping to maintain the ultra-low temperatures needed for FQHE research. 6. Hybrid cooling systems. Combining different cooling techniques, such as dilution refrigeration with ADR or superfluid helium-3, has led to hybrid systems that can achieve lower temperatures more efficiently. These systems leverage the strengths of each method to overcome individual limitations. 7. Advanced thermometry. Accurate temperature measurement at ultra-low temperatures is critical. Advances in thermometry, including the development of more sensitive and precise thermometers, have improved the ability to monitor and control temperatures in FQHE experiments. These advancements are pushing the boundaries of what is possible in low-temperature physics, enabling more detailed and accurate studies of the FQHE and other quantum phenomena. Quantum dots and energy levels. Quantum dots are nanoscale semiconductor particles that have discrete energy levels, similar to atoms. These discrete energy levels allow precise control over electron states and transitions, which is crucial for refrigeration purposes. 2. Coulomb blockade and electron tunneling. Quantum dot refrigeration often relies on the Coulomb blockade effect, where the addition of an electron to a quantum dot is energetically unfavorable unless a specific voltage is applied. This effect can be used to control electron tunneling between quantum dots and reservoirs, facilitating the transfer of heat. 3-terminal quantum dot refrigerators. A common setup involves 3 terminals, 2 quantum dots and a thermal reservoir. By carefully controlling the voltage bias and temperature differences between these terminals, electrons can be made to tunnel in a way that absorbs heat from one reservoir and releases it into another, effectively cooling the system. 4. Thermodynamic cycle. The refrigeration process can be understood as a thermodynamic cycle. Electron absorption. Electrons absorb thermal energy from the cold reservoir as they tunnel into the quantum dot. Energy transfer. The electrons then tunnel to another quantum dot or directly to a hot reservoir, releasing the absorbed energy. Cooling effect. This cycle results in a net transfer of heat from the cold reservoir to the hot reservoir, thereby cooling the cold reservoir. 5. Performance metrics. The performance of quantum dot refrigerators is evaluated based on metrics such as cooling power and coefficient of performance, COP. These metrics depend on factors like the voltage bias, temperature difference, and the specific design of the quantum dot system. 6. Applications and advantages. Quantum dot refrigerators are particularly useful for cooling small, localized regions to very low temperatures. They are promising for applications in quantum computing and other fields where precise temperature control is essential. 7. Challenges and future directions. While quantum dot refrigeration shows great potential, there are challenges to overcome, such as optimizing the design for maximum efficiency and integrating these systems into practical applications. Ongoing research aims to address these challenges and improve the performance of quantum dot refrigerators. The Coulomb blockade effect is a phenomenon observed in small electronic devices, particularly those involving quantum dots or small metallic islands. Here's a detailed explanation. 1. Basic concept. The Coulomb blockade occurs when the electrical conductance of a small device decreases at low bias voltages due to the electrostatic energy required to add an extra electron to the device. This effect is named after Charles Augustin de Coulomb, who described the electrostatic force between charged particles. 2. Quantum tunneling and capacitance. In a typical setup, a small conducting island, like a quantum dot, is connected to leads via tunnel junctions. These junctions have a very small capacitance. When the island is small enough, the addition of a single electron significantly changes its electrostatic potential, creating an energy barrier that prevents further electrons from tunneling onto the island unless a certain threshold voltage is applied. 3. Energy quantization. The energy required to add an electron to the island is given by E_c equals \frac E⁻²2c, where E is the electron charge and c is the capacitance of the island. If the thermal energy, kT, where K is the Boltzmann constant and T is the temperature, is much less than E_c, the Coulomb blockade effect becomes significant. 1. For current voltage characteristics. The current voltage, IV, characteristics of a device exhibiting Coulomb blockade show a region of zero current at low bias voltages, known as the Coulomb gap. As the bias voltage increases beyond the threshold, electrons can tunnel through the junction, and current starts to flow. This results in a staircase-like IV curve. 5. Single electron transistors, sets. One of the most prominent applications of the Coulomb blockade effect is in single electron transistors, sets. These devices use the Coulomb blockade to control the flow of individual electrons, making them highly sensitive to charge and useful in various applications, including quantum computing and ultrasensitive electrometry. 6. Temperature dependence. The Coulomb blockade effect is more pronounced at low temperatures because thermal fluctuations can provide enough energy to overcome the Coulomb gap. Therefore, experiments and devices utilizing this effect are often operated at cryogenic temperatures. 7. Applications and research. Beyond sets, the Coulomb blockade effect is studied in various nanoscale systems, including molecular electronics and nanowires. It provides insights into electron interactions and quantum transport phenomena, making it a key area of research in condensed matter physics. The Coulomb blockade effect significantly influences the behavior of quantum dots, leading to several unique and important phenomena. Here's a detailed look at how it impacts quantum dots. 1. Discrete energy levels. Quantum dots confine electrons in a very small space, leading to discrete energy levels. The Coulomb blockade effect arises because adding an extra electron to a quantum dot requires overcoming the electrostatic energy associated with this confinement. This energy is significant due to the small capacitance of the quantum dot. 2. Coulomb staircasing. One of the hallmark behaviors of quantum dots under the Coulomb blockade is the Coulomb staircasing effect. As the gate voltage applied to the quantum dot is varied, the conductance of the dot changes in discrete steps. This occurs because electrons can only tunnel onto the dot when the gate voltage aligns with the energy levels of the dot, leading to a stepwise increase in current. 3. Suppression of conductance. At low bias voltages, the Coulomb blockade suppresses the conductance through the quantum dot. This suppression occurs because the energy required to add an electron to the dot is not available, preventing electron tunneling. As the bias voltage increases and exceeds the Coulomb blockade threshold, electrons can tunnel through, and conductance resumes. For temperature dependence, the Coulomb blockade effect is highly temperature dependent. At higher temperatures, thermal energy can provide the necessary energy for electrons to overcome the Coulomb blockade, reducing its impact. Therefore, the effect is most pronounced at low temperatures, where thermal fluctuations are minimal. 5. Single electron transistors, sets. Quantum dots exhibiting the Coulomb blockade effect are used in single electron transistors, sets. In sets, the ability to control the flow of individual electrons through the quantum dot allows for extremely sensitive charge detection and manipulation, making them useful in various applications, including quantum computing and nanoscale electronics. 6. Kondo effect. In some quantum dots, particularly those with a non-zero spin, the Coulomb blockade can coexist with the Kondo effect. At very low temperatures, the Kondo effect can enhance conductance through the quantum dot, even in the presence of the Coulomb blockade. This occurs due to the formation of a many-body state that allows electrons to tunnel through the dot more easily. 7. Quantum coherence. The Coulomb blockade effect helps maintain quantum coherence in quantum dots by preventing unwanted electron tunneling. This is crucial for applications in quantum information processing, where maintaining coherent quantum states is essential for reliable operation. In summary, the Coulomb blockade effect is a fundamental aspect of quantum dot behavior, influencing their electronic properties and enabling various advanced applications. The interaction between the Kondo effect and the Coulomb blockade in quantum dots is a fascinating area of study in condensed matter physics. Here's a detailed explanation of how these two phenomena interact. 1. Coulomb blockade recap. The Coulomb blockade effect occurs in small conducting islands, such as quantum dots, where the addition of an extra electron requires a significant amount of energy due to electrostatic repulsion. This leads to a suppression of conductance at low bias voltages, creating a Coulomb gap. 2. Kondo effect recap. The Kondo effect arises in systems with magnetic impurities, where the conduction electrons in a metal screen the magnetic moment of the impurity, leading to the formation of a many-body singlet state. This results in an increase in conductance at low temperatures due to enhanced scattering of electrons off the impurity. 3. Interaction in quantum dots. In quantum dots, the Kondo effect can occur when the dot contains an unpaired electron, effectively acting as a magnetic impurity. The conduction electrons in the leads can interact with this unpaired electron, leading to the Kondo effect. This interaction competes with the Coulomb blockade effect. For a temperature dependence, at high temperatures, the Coulomb blockade dominates, and conductance is suppressed due to the energy required to add an electron to the dot. As the temperature decreases, the Kondo effect becomes more pronounced. Below a certain temperature, known as the Kondo temperature T_K, the Kondo effect can enhance conductance even in the presence of the Coulomb blockade. 5. Conductance behavior. The conductance behavior of a quantum dot exhibiting both effects is characterized by Coulomb blockade regime. At temperatures above T_K, the conductance shows the typical Coulomb blockade oscillations with suppressed conductance at low bias voltages. Kondo regime. At temperatures below T_K, a peak in conductance appears at zero bias voltage, indicating the Kondo resonance. This peak can partially or fully overcome the Coulomb blockade, leading to increased conductance. 6. Experimental observations. Experiments have shown that the Kondo effect can be observed in quantum dots by tuning the gate voltage to control the number of electrons on the dot. When the dot has an odd number of electrons, the Kondo effect can emerge, leading to the characteristic zero bias conductance peak. 7. Theoretical models. Theoretical models, such as the Anderson impurity model, are used to describe the interplay between the Kondo effect and the Coulomb blockade. These models help in understanding the conditions under which the Kondo effect can dominate and how the conductance behavior changes with temperature and gate voltage. In summary, the Kondo effect can enhance conductance in quantum dots even in the presence of the Coulomb blockade, particularly at low temperatures. This interplay provides deep insights into electron correlations and quantum transport phenomena. The Fractional Quantum Hall Effect, FQHE, was discovered in 1982 by physicists Daniel Zouet and Horst Stormer, with significant contributions from Arthur Gossard. This groundbreaking discovery was made during experiments conducted at Bell Labs, using heterostructures made of gallium arsenide-12. Here's a detailed breakdown of the discovery and its significance. 1. Experimental setup. The experiments were performed on a two-dimensional electron gas, 2DEG, confined in a gallium arsenide heterostructure. This setup involved high magnetic fields. The 2DEG was subjected to very high magnetic fields, which are crucial for observing quantum Hall effects. Low temperatures. The experiments were conducted at extremely low temperatures to minimize thermal fluctuations and observe quantum phenomena. 12. 2. Observation of fractional quantization. In these conditions, Zhou and Stormer observed that the Hall conductance exhibited plateaus at fractional values of the fundamental conductance unit \frac E⁻², h, where E is the electron charge and h is Planck's constant. The first observed fraction was \frac 1,3, indicating that the Hall conductance was quantized at \frac 1,3 \frac E⁻², h 12. 3. Theoretical explanation. Robert Laughlin provided the theoretical explanation for this phenomenon. He proposed that the electrons in the 2DEG form a new type of quantum fluid with fractionally charged excitations. Laughlin's wave function accurately described the ground state of the system at these fractional filling factors and predicted the existence of quasiparticles with fractional charge 12. 4. Significance of the discovery. The discovery of the FQHE was significant for several reasons. New quantum state. It revealed a new quantum state of matter, where electrons bind magnetic flux lines to form composite particles. Fractional charges. It demonstrated that quasiparticles could have fractional charges, a concept that was previously unanticipated. Topological order. The FQHE provided insights into topological order, a type of order that is not characterized by symmetry breaking but by global properties of the wave function. 12. 5. Nobel Prize in Physics 1998. In recognition of their discovery, Daniel Zhou, Horst Stormer, and Robert Laughlin were awarded the Nobel Prize in Physics in 1998. The Nobel Committee cited their work for revealing a new form of quantum fluid with fractionally charged excitations. 12. 6. An impact on condensed matter physics. The discovery of the FQHE has had a profound impact on condensed matter physics. It has led to further research, extensive research into other fractional states and the underlying mechanisms. Quantum computing, exploration of the potential use of fractionally charged quasiparticles in topological quantum computing. 12. The FQHE remains a vibrant area of research, continuing to provide deep insights into the behavior of electrons in low-dimensional systems and the nature of quantum states. That was all. Goodbye.